Welcome to the presentation for our final project. Our group members are Zhang and Zhu.
Our topic is generating music via the model of LSTM. This video is mainly composed of 5 parts. Let's first go to the first part, our goal. Our goal is to enrich a piece of melody by generating chords for it. Why would we like to do that? Because no matter how excellent a piece of melody is composed, it will not sound really good to the audience because with only one program, it is more or less a bit plain. Therefore, we would like to build a model that can automatically generate chords for a piece of melody so that it will have more depth and hopefully it will sound better. To do this, our model will need to capture the main traits of melodies and chords, by which I mean, for example, we need to tell which pitches are more important and which are less. More importantly, we will need to capture a feel of melodies and chords. By feel, I mean styles and emotions. This is because if you generate chords that sound really sad for a very happy melody, then that would be a problem. Now we will get into the next part to introduce our dataset and the pre-processing process. The dataset we use is Nottingham, which consists of 1035 piano pieces. 148 of these pieces are excluded from our dataset because they either contain more than 2 programs or contain notes with unusual note durations, such as frequent grace notes or tercets. These will make the next stage of pre-processing much more difficult. The second step of data pre-processing is to represent music in the form of matrix. The pieces are originally in MIDI format, which is composed of a series of note objects. Each object contains the information of starting time, ending time, pitch, and velocity of the note. We would like to convert the notes into a matrix of 155 rows. Each column in the matrix is a one-hot vector representing the pitch value in a certain time step. A time step is the duration of an eighth note. All the time steps add up together to the music, therefore the width of our matrix depends on the length of the music. In fact, each column is not a one-hot vector, it is a two-hot vector because we have both melody and chord. The first 128 rows represent pitch values from 0 to 127. Row 129 is the rest state, which implies that this time step is empty. The last dimension is the holding state, which means we have to hold the previous notes in this time step. Similar to the melody matrix, the first 24 rows in chord matrix represent the most common 12 major chords and 12 minor chords. The last row is the non-chord, which means it is empty in this time step. Let's take the note on the screen as an example. The starting time of the note is 0 second and the end of the note is 0.5 second. Therefore, the duration of the note is 0.5 second. Under a tempo of 120 BPM, 0.5 second is equal to 2 eighth notes, which is represented by 2 columns in our matrix. Therefore, what we do now is go to the 45th row of the matrix because the pitch is 45. And then we go to this row and we go to column with the index 0 and we mark it as 1. Then we go to the second column because the duration is 2 columns and we go to the holding state and we mark it as 1. Then this note is over. Then we need to finish the rest of the matrix by other notes in the MIDI file. After getting all the matrices, there is one more step. We would like to make all the matrices the same width so that we can make use of batching in the RNN model to speed up training. To describe this process, let each line on the screen represent a matrix. The length of the line represents the width of the matrix. Firstly, we need to set an upper limit and delete the matrices that are extremely long, otherwise the size of the data will be too big after padding. Here we set the limit to be 1064 time steps. 97% of the matrices are under this limit, and we discard the rest. Then we pad the matrices that are left, which means we extend them to the upper limit with 0 vectors. So far, we have finished pre-processing. We got 859 melody matrices and 859 chord matrices. which are close to 2 million columns in total.
Okay, so let's take a look at our model and approach to dealing with this dataset. First of all, we use a recurrent neural network structure. This kind of structure is really helpful for catching the time difference in terms of the melody. So each of these music would be representative in terms of time. However, there is one problem with the general RNN model, that it will have a long-term dependency. Long-term dependency means that the melody and chord that occurs 20, 30, or even a minute ago would actually affect the current status of the chord and the melody that is generated. However, in the real life, most of these music doesn't have that a long-lasting trend going on. Therefore, we adopted the long short-term memory unit. As its name suggests, it would keep both the long-term memory and the short-term memory in its check. The way it's do that is through 3 different sigmoid functions. Each of these sigmoid functions would control the cell state, as you can see on the slide. For the first sigmoid function would control how much of the previous memory would go into the next unit. The second and the third sigmoid function will be responsible for what type of new information shall be added to the cell state. Here is a more detailed look at how our data was inputted into our model. During trainings, each of the inputs would be a combination of 2 different one-hot vectors. The first one represents the current melody, whereas the second one represents the current chord. While we were doing our generation, what we would do was keeping the same current melody. However, the current chord was replaced by the generated chord from the previous one that was outputted from the previous state. This would be inputted into our model and then continue on to process them to generate a music. So this is the result for our regression. As you can see here, the training loss and the validation loss are steadily decreasing, which means there is no significant issue with our model. So without further ado, let's first take a listen to the original melody and then to the generated chord along with the melody. This is a very brief excerpt of our original melody, and here is our original melody combined with our generated chord. So from these 2 music parts, we can see that the generated chords is pretty representative of the original melody's change in terms of tones and pitches. There is no strong discrepancies between the generated chord and the original melody. There are a few further improvements we could make with our model. For one, we could detect more features from the music, for instance, its performance and composition style. These are really important in our perception of a certain piece of music. Another thing we could potentially do was to generate melodies and chords together. If we could put all of their potential combinations into a dictionary and take its value as the input, this would be more similar to a word variance of RNN. The last thing we could potentially do was to increase the versatility of the organs of the generated music if we would train with scores for different kinds of instruments, such as violins. That is everything for our final presentation, and we hope you find it interesting.